All right, so here we are in section 9.2 on infinite limits and limits at infinity. So we'll be talking about infinite limits, of course, locating vertical asymptotes, limits at infinity, and finding horizontal asymptotes. All right, so here we go. Infinite limits and vertical asymptotes are used to describe the behavior of functions that are unbounded near x equals some value a. Now, the limits at infinity and horizontal asymptotes are used to describe the behavior of functions as x assumes arbitrarily large positive values or large negative values. Now, infinite limits and vertical asymptotes help describe the behavior of functions that are unbounded near that x equals a value. Now, we illustrate this with the function f of x is 1 over x minus 1. Now, at this point, if we have x is equal to 1, that's going to give us a 0 in the denominator, and we'll divide by 0, which is not possible. And so that means there's probably going to be a vertical asymptote at that point. And if we graph that, what happens is we do have that vertical asymptote at x equals 1. And so this is what the function would look like in blue. And so there's no real number L that the values of f of x approaches as the x approaches 1. So as we get closer and closer to the 1 from the left side over here, we see that it's going towards negative infinity. And then as we approach from the right side, it's going up here towards positive infinity. Okay, and so that gives us that vertical asymptote. Now, this table here, table 1 and table 2, here we're approaching x um, from the right side. Okay, so we're going closer and closer and closer and closer to 1, which would be, the actual vertical asymptote. And so we start at like 1.1, then we add a 0, and then 2 zeros, 3 zeros, 4 zeros, 5 zeros, and then we plug it into the value. And what we see is it's getting closer and closer and closer to as we would go up positive infinity. And that's what we would see by the picture as well. It just keeps going up, and we're getting closer and closer, up higher, and it's just going up. Now, as we approach from the left, we're starting at 0.9 and 0.99, 99999, and so on. And as we can see, each of those values we're getting closer and closer to negative infinity. And so that's what happens in that case. And so graphically, we see it this way, and in a table method, we can see that this goes to positive infinity and this one goes to negative infinity as we approach from the left and the right. Now, we write this symbolically as limit of x approaches 1 from the positive side of 1 over x minus 1 is equal to infinity. And, or I guess I should say, f of x equals 1 over x minus 1 approaches infinity as x approaches 1 from the positive. Now we write it as limit of x approaches 1 from the left of 1 over x minus 1 goes to negative infinity, or f of x is equal to 1 over x minus 1 approaches negative infinity as x approaches 1 from the negative side. Now, such limits are called infinite limits. Now, the symbol infinity is used to describe positive growth without bound, and the symbol negative infinity is used to describe negative growth without bound. And hence, we saw that, one was going down without bound, and the other one was going up without bound. Okay. Now, since the limits go to infinity, the limit actually does not exist. So definition, infinite limits and vertical asymptotes. So the vertical line x is equal to a is a vertical asymptote for the graph of y equals f of x if f of x goes to positive infinity or negative infinity as x goes to positive or negative a, or it goes to a from the positive or the negative side. So that is f of x is either increasing or decreasing without bound as x approaches a from either the right or the left. Okay. And again, that's kind of what we saw with the thing here. So as x approached a, which, this is going to be our a, from the left, it's going closer and closer to negative infinity. So it's decreasing without bound. Now, as we approach a from the right, we're going up without bound. So we're increasing towards infinity without bound. And so that's how that works. Now, locating vertical asymptotes of rational functions. So if f of x is equal to n of x over d of x, and it's a rational function, d of c equals 0, and n of c is not equal to 0. So this is not equal to 0, but the d of c is, then the line x equals c is a vertical asymptote of the graph. Okay, so wherever that that d of c is equal to 0, that's going to be a vertical asymptote. Now, polynomial functions have no vertical asymptotes. So vertical asymptote of a rational function only occurs where 0 is in the denominator. So, like we had that 1 over x minus 1. Well, at x equals 1, that was our vertical asymptote. Okay. All right, so if f of x is equal to n of x over d of x, and both n of c equals 0 and d of c equals 0, then the limit of f of x as x approaches c involves an indeterminate form, and theorem 1 doesn't apply. Okay, so if we have the f of x can be split up into n of x over dx for rational, and it gets 0 over 0 as the indeterminate form, basically, we're going to have to simplify this using algebra. So usually what we're going to do is we're going to, reduce it if we can cancel things like that to make it so it works. And then we can get it into a form where, theorem 1 will apply. So that's kind of the key, is we're going to have to use algebra to make it so we get it so we can use theorem 1. All right, so let's pause there and we'll come back with some examples.